Topic 4 centers on reservoir simulation. And as I mentioned in class, reservoir simulation is a very broad topic, right? As a graduate student, I took 4 different courses on reservoir simulation. So we will not be able to go through all of the aspects of reservoir simulation, but what I will do is to introduce some of the basics you need and then steer you in the direction of reservoir simulation using MRST. I've already uploaded some videos from PETI 4056, like I mentioned before, and those also go into a little bit of more details on some aspects of reservoir simulation that I believe is important, especially if you haven't taken a reservoir simulation course before. I believe you all know why reservoir simulation is important, so I'm not going to spend more time on this. I'll go quickly through it. It's important because it can be used to optimize production and also to optimize the economics of an oil and gas field. So when you're optimizing production, you can be optimizing cumulative production or cumulative oil production or cumulative gas production. And then when you're optimizing economics, it could be NPV or say internal rate of return, but we mostly focus on net present value. And you will see sometimes the results that give you the optimum net present value is not the result that gets you the optimum cumulative oil production. Why? Because the cost of achieving certain cumulative production might outweigh the profit you make from that improved oil production. For instance, drilling more wells typically will give you more oil production, but the cost of the well may lead to lower net present value. So some of the other things you can do with a reservoir simulator is you can simulate different recovery mechanisms like water flooding, gas flooding, steam injection, and so on the same field, right? Because it's a numerical model, you can run different scenarios and then you can figure out which one gets you the best enhanced oil recovery. So you can select the appropriate enhanced oil recovery mechanism to use by simulating different recovery mechanisms. You can optimize the number of wells to develop a field. This can be done using an algorithm, an optimization algorithm, or using trial and error, which you will surprisingly see most people do. You can also find the best location for a well using an optimization algorithm or by good old trial and error, which is not recommended. You can also spot good locations for infill wells. So you already have some wells in your reservoir and your manager asks for the best location to drill one more well to get you the best net present value. And so some will do trial and error, trying different places based on the saturation, right? But you can also use an optimization algorithm to find you the best infill well location. Reservoir simulators are important because you can use them to estimate reserves and their time-dependent production profiles, because it's not all about the reserves, right? How quickly you get the oil could be even more important, because net present value is dependent on time, because you're going to discount the recovery basically through time. I should say the main reason is because of the time value of money. $1 today is more than $1 in 10 years' time. So your reservoir simulator can be used to get you not just the final estimated ultimate recovery, but it can give you flow rates or cumulative production against time. You can use the simulator to quantify the uncertainties in the estimates of cumulative oil production rates and so on. Why? Because you can use several input parameters sampled from a distribution, and then you get a distribution of the quantity of interest like cumulative oil production. You can use simulators to provide support for economics and operational decisions for an oil and gas field, like deciding what recovery mechanism that should be used to get the most net present value, for instance. You can use simulators to understand the effect of several reservoir parameters, like what happens when you increase permeability, when you reduce porosity, and so on. You just simulate it with different values of the quantity of interest, and then you can get the sensitivity of the model output variables to certain input variables or reservoir parameters. And you will see that many regulatory bodies like SEC and banks that will provide you with funding, they want to see your simulation model results. They don't want to see, in many cases, they don't want to see your decline curve analysis, because those could be subjective, right? Your initial flow rate, especially your B and DI, could be subjective. So reservoir engineers can jack with this so that they get certain results which will appear to indicate they get more cumulative production. And that's why they want to see simulation-based results, because those are not as subject to bias as decline curve analysis. Here I'm going to go quickly through the continuity equation. I already uploaded the video from PERI 4056 that goes into all of the details. So I'm going to sketch how you derive this continuity equation here, but I won't go into as much of a detail as I did in that video. So go ahead and watch it. The continuity equation is a statement of mass balance. And if we pick a cell from a domain, right, very small, infinitesimally small cell, which will be small enough to ensure truncation errors are minimized. And then we focus on what is going into the cell, which are these rates. I mean, these are fluxes, right? Rho U is flux. We talked about that. To get mass rates, you need to just multiply this by the corresponding area. So for this guy, you're going to be multiplying by this area. And for this one, you'll be multiplying by the area of this face, right? And for rho UI, you're multiplying by the area of this face. How do you get those areas? The length in this direction will be delta Z, the length in this direction delta X, and the length in this other third direction will be delta Y. And those are the parameters that get you the area, and then the product of those three gets you the volume of the unit cell. Good. So we know the rates. We can get the mass rates in by multiplying these by areas and summing all three together. And then we can get the mass flow rate out. So we are working on this expression of mass balance. Rate of mass flow in minus rate of mass flow out equals the rate of mass that is accumulated within the representative elementary volume. And that's because mass is always conserved. So we are deriving a mass conservation expression. And then if you have a generation term within the cell, which is the source or sink, you can add that afterwards. So we will ignore this for now, and when we're done, we just put it in on the right-hand side, or you can put it on the left-hand side with a negative in front of it. So I already talked about rate of mass flow in. So it's these guys multiplied by their corresponding areas all added up, right? And then you will take out the rate of mass flow out, which will be these three guys, 1 multiplied by the corresponding area of that face, plus this guy multiplied by the corresponding area of that face, plus what is coming out on this other face multiplied by the area of that face. And so you will realize that these terms will also show up in the mass flow out. So basically you have these three terms subtracted from, maybe I should write it briefly. So rho ux, what's the area of that face of the ux area? It's delta y delta z plus in the y direction, and that is this face, which is delta x times delta z, right? Plus rho u z, the last one, and it's delta, where's the z direction going down, so this phase is delta x, delta y. So those are the rate of mass flow in values. And then you will subtract out these three terms. So I'm not going to write those three out, multiplied by their corresponding areas. And what I was saying is you will see this term is going to cancel out this first term. And this guy cancels out this term. And this guy cancels out the last term. And all you're left with is negative of this guy multiplied by the corresponding areas minus this guy minus this guy. So those three negative terms will be on the left-hand side. And the right-hand side is the rate of mass accumulation, which is basically d dt of phi rho. And then when you divide both sides by the volume, which is delta x, delta y, delta z, you're going to see the terms that are kind of like this. When you divide this by the volume, delta y, delta x, delta z, these two terms in the minus delta rho u x term is what is left, right? You're going to have a delta rho u x divided by delta x, and so on. And that basically gets you this term right here. Go ahead and watch the videos and you will see the details of that when you watch the video I already uploaded. And in the continuous form, so when you assume delta x, delta y, delta z tends to 0, right? They become infinitesimally small. And you assume delta t tends to 0, then you have the continuous form. When you're done deriving, you have the discrete form, right? And then you make these assumptions in the limits, and then you get this continuous form here, which is the continuity equation. And that's the basis for reservoir simulation. All we need to do to get the governing equation for single phase flow in reservoir simulators is to substitute Darcy equation for velocity in here. And that's the equation we solve in reservoir simulation.